Hi everyone, welcome to Deep Learning for Natural Language Processing course. The recording will be great for this. Class today will go over neural machine translation. We'll give a hint on how machine translation was before deep learning and deep neural architectures. And this will motivate us to talk about pretty much one architecture and one technique. Sequence-to-sequence models, and also attention, which is, I would say, it's used virtually on any sequence-to-sequence. Nobody uses just sequence-to-sequence models nowadays. Machine translation. So machine translation together with text summarization, and again, if we're talking about high resource language, it's one of the holy grail problems in artificial intelligence, and more specifically in NLP. So machine translation, text summarization, dialogue systems now is debatable because of AI assisted models. Not only because the task itself is quite challenging, but also because of the valuation. And this we'll see later on when we talk about text generation and summarization. To evaluate these tasks are really, really hard, simply because the way we evaluate them doesn't reflect human behavior or human assessment. It is a proxy. Nowadays also, we have better metrics than BLEU, Meteor, NIST, word error rate, Rouge, and so on. But they're still a proxy. You can still game those scores pretty easily. Hopefully you remember Warren Weaver. He also was quite active in machine translation to some extent. So how he defined machine translation. So one naturally wonders if the problem of translation could conceivably be treated as a problem in cryptography. When I look at an article in Russian, I say this is really written in English, but it has been coded in some strange symbols, and I will now proceed to decode. So this idea of decoding a symbol that you don't know how it looks like or what the relationship is, it's pretty much the problem of machine translation. Of course, in practice, is not as nice as is right here. Hopefully, we'll be able to show, including some problems that we have with machine translation. So what is the task, pretty much? You have in this case, you have a source sentence. I like eating cakes, and then you translate that to Ich esse gern Kuchen, eu gosto de comer bolos, me gusta comer pasteles. If you're lucky enough, things will align. And that's really nice because you have one-to-one translation. So I is ich, eu it has some inflection, it's me, like, gern, gosto, gusta. So these words are aligned. However, that's not actually the case for a bunch of scenarios, and we'll see some of them. Okay? Another way for us to take a look into how machine translation is, or translation, the task is itself, is through the Vakuo pyramid, in a way that we're trying to move from either from words, a syntactic structure, a semantic structure, and one source language to one target one. And translation, it can occur in different steps on this structure. So you can move directly from word to word if you have this alignment there, and if you have this one-to-one translation. You can use a syntactic structure. In this case, you have to deal with word disambiguation, or sometimes you translate a sentence, the meaning of that sentence into another meaning. In this hierarchical model, there's also this interlingua, which is supposed to be something as high level that every language should be able to be translated into that, and this should be common to all the languages. This is debatable. There was some attempt to do this with, how was that language? On the internet, they tried to propagate that. It was not working. Esperanto or something many years ago. But be that as it may, why machine translation is quite hard. we have some problems with that. One of them is syntactic and semantic ambiguities. Imagine that when we're talking about words in the same language, we already have problems in disambiguating their meaning. Imagine now that you move this to different languages. And when I say different languages, think also outside the box, not necessarily just natural text. You can have code or signals for that matter. Although code is way less ambiguous than language per se, but in any case. Also, morphological issues with agglutinative languages with complex word structures. Some languages, I think we showed that in the second class or the first with Turkish, also with German. As you keep putting the words together, it's hard for you to break it down. Also, the syntactic variation between subject, verb, and object. In English, we have this order, subject, verb, and object, but some of them, they don't follow this structure, which make things a bit complicated when you translate it from one language to the other, because that might change the meaning. Just to give you some idea how this syntactic variation looks like for us. So in subject, object, verb, we have she, him, loves. If we have subject, verb, and object, we have she loves him. This is somehow closer to our language. And then you have loves she, him, loves him, she, him loves she, and things start to get kind of confused, even for us to read. Imagine for you to code that. And I'm pretty sure there are way more other complex structures than this. This is just a snippet. Yes? Oh yeah, this is a really rough estimate and how languages, non-languages, they are categorized between this syntactic structure. But I highly doubt that this is considered low resource language. So if you consider English, German, Portuguese, Spanish, and so on, they are divided. This is the division that they have in this structure. Okay. So what is a good translation? It's pretty much what we have for a good language model. If a translation is faithful and correctly conveying information and tone, it is debatable also, of the origin sentence, this is a good translation, and of course it should be fluent, otherwise it's not a good translation. So what are the origins and how things actually work out for machine translation back in the day? And hopefully we don't propagate this that much, but again, NLP is always divided in three parts: rule-based systems, machine learning with statistical features, handcraft features, and then neural network architectures. So around the 50s, things used to be solved with rule-based systems, a lot of rules, and very cherry-pick rules and cherry-pick alignments, which was also a big problem. So systems were mostly using this very specific rules to create this bilingual dictionary to try to map one language to the other. Just to give you, later on, if you have time, this video is like 5 minutes, you can take a look what are the problems. And people, when they were using machines to do machine translation, they were already saying that, yes, if you have to translate technical terms, this will be done in the next 5 years. Haha, was definitely not. But now it's kind of. But poetry and more creative text, this is hard to do, and we, as in that time, don't think that this will be possible. Things change a bit, but just to give an example, because of this cherry-pick alignment that they had in words, things like, if you would translate the spirit is willing, but the flesh is weak to Russian, and then you get back to this translation to English, because of the words that they use, this sentence here, the translation would be, the liquor is good, but the meat is spoiled. So not actually the meaning that we're hoping for that. But yeah, they have a bunch of other examples. So moving on to the 90s to 2010s, the idea was pretty much to learn a probabilistic model from our data, a lot of data, And then suppose we're translating German to English. Pretty much we want to find the best English sentence. Why? Given a German sentence acts as our context, whatever the size of that sequence is. So in other words, and we can wiggle this around, and pretty much you would have two models. One translation model that models how words and phrases should be translated, and you learn this from a parallel data. And this is done since the dawn of days, pretty much. We still use a lot of parallel data, in fact. There are ways to cope if you don't have aligned parallel data. You can create them relatively easy, really between quotes. And on top of this translation model, you also have a language model, which is pretty much what we have done so far. So this model, how to write good English and learn from normal monolingual data, okay? Just to give you some idea, and again, every single class that talks about machine translation, they will talk about Rosetta Stone as well. This is one of the very first attempts to kind of align and produce, not exactly align, but to produce a parallel data in which you would have ancient Egyptian, Demotic, and ancient Greek. And this idea to use text in different symbols and different codes to convey the same meaning and explore these relationships for you to have some sort of translation. People have using this for quite some time. There is a twist on this. On top of parallel data, you still have to deal with alignment. Sometimes this works, most of times this does not. Not only from different languages, from the same language as well. When you're, let's say we're working with paraphrase generation or paraphrase detection, which is pretty much the same language in the context. It's not likely when you paraphrase something in your assignments, in your report, in your thesis, you have a one-to-one word on what you're reading. You have an idea and you transform that into a different sequence, and so you don't have alignment there as well. So it's ideal to have alignment, but it doesn't happen in practice that often. And how we incorporate alignment. So we actually want to consider what is a sequence target that we have here, an X, given our context and our source language, with whatever alignment that we have between those two languages in this case. And you have different models how to deal with this. You can work with phrase-based models, or we can use word-based ones, but we'll talk about word-based ones. Well, so yes, alignment, and I don't think I need to say this, but it's the correspondence between particular words in the translated sequence pair, and it must be obtained or learned either by manual alignment, or you try to enforce this semantic alignment. Let's say, well, before I give you the solution for this, can you think about the semantic alignment between different languages automatically? Can you think about we learned this approach, by the way. Let's say I have different languages and I want to align what different languages they mean. How do you put this? How do you align them? Huh? Not necessarily going to have different language, the same part of speech, in the semantic level to make it a bit easier. Which technique we learn how to transform a set of words, a bag of words, a corpus, into some vector representation? Exactly. So if you do different models for different languages in a set of corpora, and you, let's say, use the vector space representation from those words in different languages, if they have the same meaning, hopefully there will be some sort of alignment between those words. And actually people have done that. In 2016, 17, if I remember correctly, Google did this, and they found a really good overlap. They use Wikipedia pages. Most likely will have the same Wikipedia page in different languages, and they found out an overlap between Japanese, Korean, Portuguese. There's a fourth language, but I don't remember right now. So they were able to provide this rough alignment of semantic without actually saying this word here is this word there. It was actually pretty cool. But coming back to machine translation, some examples how alignment is not that straightforward. Let's say you have some words have no counterpart, like Torschluss Panik. How you translate that? Huh? So, according to my notes, fear of gate closing is a fear of something is about to finish or end, and then you have this. Well, that's the internet saying, not me. However, we have some more, let's say, concrete examples and how things do not align that clearly. We can have many to one, like die, das, and der. They all go to the. This is somehow easy to solve. It can be one to many, like bitte, and then it can be many to many, like machen, tun. And on top of that, we have doch, which, how you translate doch? It has 5 meanings, by the way. Or halt, eben. How do you translate these things? Mal, in a sentence. Yeah.
I think it also depends.
Mm-hmm. It's really hard when you have those words there. Also. And this is also subjective. I mean, people might understand this translation differently. So imagine if to people it's already hard, imagine putting this into a machine. Not fun. So how we do with statistical machine translation, we could enumerate every possible target sentence and calculate their probability. Needless to say, that's the same problem we had with language model. This is simply too expensive. If you have to compose every single possibility, it's not feasible. Or we can use an heuristic algorithm to search for the best translation. And this is actually, heuristics, they're used most of times every time you have to generate something. Either a new sequence or a possible chat dialogue system, new text on text generation. We use things to prune and trim how much or how are the most interesting ones you're generating. We'll go over some of them when we talk about sequence-to-sequence models. Okay, so statistical machine learning was a huge research field, and the best systems were extremely complex, and I cannot stress this enough, how many rules they have for very specific cases. Systems had a bunch of different subcomponents, a lot of hand-featured engineering. They use a lot of external dictionaries, lexical databases, table of equivalent phrases when things don't translate automatically between them or you don't have a natural alignment. A lot of human effort to maintain those, and not to mention that you would have to do the same task between quotes for every single language pair that you had. In other words, it would not scale. So what happened? And this really nice anecdote is not from me, but I really like how they portray that. So then neuro-machine translation happened. And to give you an idea how fast and how complicated, let's say, how fast-paced it was, imagine that this is a statistical machine translation. And this happens. This is neuro-machine translation. Needless to say, what happened with the field, right? I hope I don't hurt anyone's feeling, but this pretty much killed statistical machine translation like in the space of 2 years. Again, if you're working for low resource language, things are a bit different, but still, it killed the field. Anyways, with neuro-machine translation, the field, it changed again, simply because we found a way, or we found an architecture to train end-to-end, and this architecture would be able to scale for any kind of language you want, as long as you have data. As long as you have data, hopefully some parallel data, you'll be able to do this. And the idea is to use this neural architecture. It's called sequence-to-sequence. People don't actually use vanilla sequence-to-sequence nowadays. They use with attention, and then later on we use with self-attention and so on. But the main idea of sequence-to-sequence, how you can look from the second part to the first part in the conditional matter, this is actually quite important for us to understand what comes next. And the idea of to use two neural networks, it can be of any type, LSTMs, bi-LSTMs, transformer, GRUs, and so on. And I think I mentioned this before, when we talk about machine translation, don't think just for natural text to natural text. The same, now that we're moving from this architecture this scenario, this paradigm, that we need to know all the rules from a language, now this is really, between quotes, this is irrelevant because we have enough data to capture those relationships. You can apply to any kind of sequence you have from input and output. So if you can correlate this, even words from the same language, text to text, let's say you want to summarize a text from a large sequence to a smaller one, or you want to transform code into natural text, or the other way around, or codes with different kind of languages, and so on, or recipes, and there's literally limitless possibilities with this. And then we'll talk about next class about sequence to sequence, not next class, this class, about sequence to sequence, and later on also about attention. So as we were talking about how we can combine two neural networks to come up with this new architecture that will help us in neural machine translation. Last class, we were talking about how statistical machine translation was substituted or overpowered by neural models or neural machine translation. Okay, so neural machine translation is a way to do machine translation with a single end-to-end neural network. So instead of us taking care of all those alignments and handcrafted features that we're talking before, now we'll simply use two architectures, two neural networks. It can be for any type. We'll play around with RNNs, but it can be two LSTMs, two GRUs, and so on. And we'll pretty much obtain the same thing that we had before with statistical machine translation, but without getting into details such, okay, how can we align these things? Or how can we account for how much of the context we have? I mean, we'll do this kind of automatically, so there's no need more for us to do this by hand. Some applications that we can have for this sequence to sequence, and this is still used a lot today on a more text-to-text fashion. We can use, and I think we mentioned this before, we can use this for summarization, such as long text and short text, dialogue, previous utterances and for the next one, parsing, code generation, anything that you can organize either your training activity or pre-training for that matter, and you can combine this in two sequences or text to text, input and output. You can use this architecture and it's quite powerful. We will go over the vanilla sequence to sequence. Nowadays, people don't use that anymore simply because they're more powerful architectures, at least in NLP. But we'll take a look in some of them, right? So how the sequence to sequence model works. You see a lot of similarities, and hopefully you see how we're simply building up on a new, let's say, block on everything that we learned before with RNNs. It's pretty much the same thing. So we're gonna have an input source, and then we're gonna code this with whatever embedding that we have. And then for the first part, we'll have this encoder RNN. And again, we are using here RNN just for the sake of simplicity. We can use any architecture here, right? And then the idea is the same way we're doing language modeling before, in which we carry out the hidden states from the previous layer to the next one. We'll do this for the entire sequence in this first part, as we call the encoder. And then the idea is to transform this input into a target output. So we're going to start decoding or derolling everything that we coded before here into a language model fashion. So instead, if you remember correctly, when we were doing language modeling before, we had a artificial hidden state in which we'll simply ultra-aggressively predict the next word over and over again. Now, instead of us starting from scratch or with some random values, we already encoded, hopefully, enough meaning, enough relationship between words, so we don't have to start this from scratch anymore. So our previous hidden state is going to use the entire context that we have for whatever input source that we have had before. And the idea is, after I have this, this first part here on the left coded, I'm going to start predicting the next words the same fashion as we had it before. And this part right here, it's simply using another recurrent neural network. So from our previous state, which is the entire sequence right here, we have a start which will pretty much, and this idea of using a special token to say, okay, this is where things start or where this end, and mark, let's say, the break between sentence and so on. This is still used today a lot for the transformers architecture. When we see BERT, we see that they still use special tokens to do this. When you want tag positional encoding for more fancy architectures and so on. So this idea to use a signal to give a hint where things should start or where things end, they're still used today, which is pretty cool. But in any case, and then after we have our initial state right here, we start decoding or predicting the next word all over again. So in the first start here, I know that the first word is I. Hopefully with training you get into this. Although this here is test time, so after I generated I provide I as my input, and also all the hidden states that I had before. For the next one is like, so I put like as an input here, and again, the previous states from this neural network here on the right that we call a decoder, and all the previous states that were in the hidden states from our encoder. And then on each step on our decoder until we hit a specific end token, we'll simply take what is the word with the max probability or the highest probability that makes sense to be here as the new sequence. All right? So the encoder, RNN, or this part here on the left, produce an encoding for of the source sentence from our input. Hopefully you can already see some concerns about this architecture. Imagine that we have to encode everything here. And our decoder is nothing more than a language model that generates the target sentence or the word by word given all this context that we have here. All right? Yep. The very last state from our encoder encodes the source sentence as a whole. So hopefully, when we get to the last state in our encoder, we'll be able to capture, let's say, a good representation for the sentence to use as a context in our decoder, right? Our sequence-to-sequence model is an example of conditional language model. Why? The language model, because our decoder is not doing anything new. It's simply predicting the next word over and over again according to the previous state. So it's 101 language modeling. But it is conditional because its predictions are also conditioned on the source sentence X. So before we had the probability of X given Y, our target and source sentence, we wouldn't have this second parameter here, this X. So for every new word that we have in our decoder for our Y here, you see that we are carrying out all the encoding from our encoder part, so represented by this X. And a natural question is, of course, how do we train the system? As before, you need a parallel corpus, somehow align with input sequences, input sentences, and output sentences, right? And I think that's it for this guy. So, and how training it works for us? So we still have the two sequences, but the difference is we don't need to actually use the predictions that we have other than just calculating our loss. We can simply use the actual word when we are trying to predict what the decoder should output for us. Pretty much the same way when we were doing language models with RNN. So instead of using the actual prediction, it could be some gibberish. We use that to calculate, okay, how far away we are from this target sentence that we're trying to predict, but at training time we actually use the actual word that we have aligned from our corpus, the source sentence, and also the target sentence. All right. The cool thing is, even though we are using two sequences for this, or two RNNs, the training, the optimization for this is done from end to end. So we backprop from, let's say, the very last state from our decoder, sorry, and to the very first state in our encoder. So the backpropagation operates end to end. So you don't have to take care, okay, I will do optimization for one part and then I do another one for the second part. This is simply done automatically for you. And then how do we guarantee that given whatever representation that we have for our encoder, I make sure not to produce some trash? Because this is a bit hard to control, right? One approach for doing this language model on the decoder part is simply use greedy decoding in a way that we simply optimize for the max probability on the next word given whatever input that we have. So we don't care about, let's say, if it's not the top one word with the highest probability, we simply discard everything and take that first one, and let's go with that. Can you see some problems in going greedy when you're simply predicting the next word based on whatever max probability you have? Or, I mean, not just with this whole, let's say, linear paradigm. Can you see a problem with this? Well, to begin with, there is no guarantee that the word with the highest probability will provide you the sentence that makes most sense. It can happen, of course, but it's not necessarily the case, especially for specific corpus and context. Also, no undos. So this architecture here is not that flexible in a way that you cannot choose to go back after you generate the next word. So once you generate, let's say here, from the start it's I, and then from I you predicted like, and so on. You cannot go back because in the end it was I like to eat computers. So yeah, too bad, that's what you get now. So it's a bit hard to control for that. All right? So an alternative for this, we can do exhaustive search in a way that we maximize the probability for the entire sequence. Given at every new word, we simply exhaustive look for the entire sequence, consider the entire vocabulary. Needless to say, this is not very efficient simply because on each step we have simply too many possibilities. We pretty much have the entire vocabulary, and this is actually, it doesn't work for us. It's simply too many possibilities. All right? But hold on, there is a way to take care of this. One way of doing this is using Bing search. And what is essentially is a fancy name to say we're going to start a couple of possible sentences. The one with the highest scores given a certain number of sentences we keep, and then we choose the best one based on their score. How many sentences we will initialize, or we're going to do the entire sequence, is up to us. This is a free parameter, so you can control 1, 2, 3, 4, 5, 10. It depends on how much computing power you have, of course. In practice, this number is around 5 to 10, and pretty much the idea is we're gonna keep track on every, let's say, on every time we expand the most, let's say, probable words that we have for that sequence, we're gonna keep only those with the highest scores. Is this guaranteeing for us the best sentence or the best result? Not by a long shot. But it is better than doing greedy, and also, I cannot stress this enough, it's way better than doing exhaustive search. And you might think, but first, let's go over the Bing search, and then I'll tell something that was nice, was published last month on large language models using chain of thought. It's really interesting, but we'll get there. So, how Bing search work, and by the way, this is also used in chat dialogue systems. Text summarization is not exclusive to machine translation, right? So, how this works. We have a Bing size of K2. Of course, in practice, this does not work. So we have our start sequence right here. By the way, are you seeing this shadow? Okay, there's a fly here. Okay, sorry for that. So in the beginning, from our start sequence, we'll simply start 2 because we don't have anything right now. We just take the top 2 that we have in our probability, starting with the start symbol. And then we have the highest scores associated with that, so there is nothing to choose. You simply continue the 2 with the highest score. After we do this, on each of these new steps, we also expand with a bin size of 2. So from I expand to I feel, I like, and from you can, you say, and then we keep doing this now only for the top 2 on this, considering the score that we have for the probability of this entire sequence. So in this case right here, we continue from I like to. So we continue on 0.8, and then here we continue with minus 1.2. And I didn't mention this, but the values are negative, but it doesn't matter that much. For the next step that we have, again, 4 possibilities right here, we keep those with the highest scores, so 2, in this case here, C. And then we keep doing this until we finish our sequence. Well, I think I put this in the next slide, but we continue the sequence or the K sequence until we finish. And how we finish that? By providing the end token or a specific number of steps, and of course, the sentence that we pick to represent whatever sequence that we're trying to predict is simply that with the highest score, given the entire path that we have and whatever K possibilities that we chose to develop. And you might think, well, that's pretty dumb. Why people still use this? You'll be surprised. How many of you already work with prompting on those large language models? Prompting is you provide a text and say, hey, provide for me an outline for a lecture. And then it provides, and then you get back to this, improve that because it doesn't make sense, it's trash. And then you keep improving over again. This is prompting. When you ask a language model to do something, you provide a text, and given that input, you will be provided by an output. So this exercise of back and forth with this large language model is called prompting. And even though those models are super complex, they have billions and billions of parameters, now it comes to the point is, how do you exercise this chain of thought that you have with this prompting in a more performatic way? You might think, yes, they come up with different fancy architectures, but actually there are recent work providing that if you do simply a Bing search with that, it can get you really far in a way that you provide your language model a prompt specifically, and then it provides the top 2, 3 responses, and you keep developing the one that maybe immediately on the next step, it might not be optimal, but along the way with that chain, it might provide you the highest score. So it's really cool how something that was developed quite a long time ago is still being used today. But in any case, I can provide this for the reading. I'll provide this on the lectures about transforms, I guess. But be that as it may. When we stop developing our sequence, in grid decoding, we usually decode until the model produces the end token. So as we saw, we have a start token, the sentence, and the end token. And in Bing search decoding, different hypotheses, they may produce this end token depending on the sequence that you have. So either you go further, a longer sequence, or a shorter sequence, you can have your end token there at whatever point. When this happens, simply you put the sentence that was completed aside and you continue the other hypothesis. And there's ways to, let's say, to build on top of this. You can start with a specific number of sequence, and if one of them already gets the end token, you simply start a new one that was, let's say, the top 3 or 4 that was previously not developed. There's improvements and improvements on this architecture, all right? But usually, what happens is you do this for specific timestamps. So you have a cutoff, I don't know, after 10, 20, or whatever number steps you develop. After that, you cut whatever your sequence that you have. Or if you have at least a specific number of complete hypotheses. Let's say you keep developing them until you reach the end of 2 or 3, and that's it. All the others you drop. Okay? Some concerns, when we were developing the sequence, on Bing search, you probably saw that we want to maximize the score that we had there. The thing is, the longer your sequence gets, the lower your score gets, simply because you account for all the probabilities in all the states. So how you cope with that? You simply normalize that in a way that you don't have to penalize longer sequence because of the score if you take into account their length. Otherwise, all the, let's say, all the short sentence or the short sequence, they will have a higher score, and you will always have short sequence being developed. Yep.
In this case,
Mm-hmm. Mm-hmm. Usually, when we're trying to decode this part, you have a source sentence. So in this case, you have a training set that you know exactly when that sentence is until it's going to be developed. You have the end token at training time. On test time, probably you have to develop this a specific number of steps, or until you until you reach a specific threshold on the score function. But if you don't have any stopping criteria, this will develop endlessly. Of course, all of them, they have some cutoff. At some point, you have to stop it. But that's pretty much how it is. Okay? This is a good example how these models, if you continue those sentences endlessly, you see these models usually hallucinating. Like in the beginning, when you have short sentence, say, hey, it makes a lot of sense. And then after a while, it starts providing some gibberish, and it doesn't make sense because the longer the sequence, specifically talking about vanilla sequence to sequence, the longer your sequence is, you are relying way more that in the very end in your encoder, you have that sentence, as long as it gets, it will be represented in the last state. So there is no guarantee that every single step before, it can be used to produce a sane sentence towards the end. But it's not trivial to do this. It's a bit annoying, okay? Some advantages with neural-machine translation compared to statistical one. We do have a lot of advantages. First of all, we have better performance. The output that we have is more fluent. Needless to say, you can scale a lot simply because now you don't need to develop, let's say, specific rules for every pair language that you have. If you have enough data that you can align between input and output, you can explore that and scale as many languages as you have data. All right? Better use of context, that is debatable, but in theory, you're making a smart use of your context because you encode the entire input sequence as a context for everything that you were developing before when you were decoding. But if that's the best one, that's debatable. We'll talk about this in a minute. Better use of phrase similarities, simply because you have this aligned pair. You don't know exactly how each word will be aligned back and forth, but at least on the sentence level, you know that one input is related with that output regardless. We have a neural network to be optimized end-to-end, so there's no individual subcomponents that we have to take care. I don't know, there's specific, although you can include this in your model, you can include external knowledge through lexical databases, dictionaries, Wikidata, and so on, but in this version, vanilla one, you don't have to worry about these individual components. Also, needless to say, it requires way less human engineering effort, and this is one of the breakthroughs. Like, you don't have to take care now with every single detail that we had before with statistical machine translation. And in fact, this is most true for, I would say, most architectures that we see here. In the beginning, you would see that neural architectures, they wouldn't perform that well, but they allow you to scale. And this is really a game changer from now on. But don't think this is just flowers. There are huge problems with every single architecture. We try to provide, okay, it's good because of that, and it's also is bad because of that. In case we miss, let me know, and I can include that for sure. But some disadvantage with neural-machine translation is it is less interpretable, simply because we don't know exactly, for example, what those weights they mean. there's no way for you to pinpoint that, yes, this matrix and with this weight distribution here is taking care of whatever nuance that we have in between those two sentences. Also, it's difficult to control in a way that you cannot easily specify rules or guidelines or how you're translating, how far you're translating, what you have to include, what not to include, idioms, cultural aspects. You cannot do this. Also, safety concerns. I mean, it's not easy for you to prevent a model simply to output something. Let's say it's a touchy subject, for example. And this actually is still a problem for up-to-date ultra-aggressive models that produce any text. What happened in practice is, instead of taking care on the inner components of taking probabilities of words, let's say, that might represent some stereotypes or something, they do most of post-processing. After they generate a sequence, if that sequence for whatever reason should not be used, they cut that or they eliminate or they provide a message. I don't know if you ever play with the very first versions of these large language models, they would output some really nasty things. Of course, this is related with the data they were ingesting, of course, but now either those models, they're capped, or simply you have some comments as disclaimer, say, hey, the output might contain whatever words and so on. But we'll see more about this when we talk about text generation in the very last class, when we talk about ethics and bias in this lecture, right? Also, there are other problems. The decoding part is a bit inefficient. If you have some error or whatever, because of the training data that you have and the prediction is not good, you will propagate that. Words out of the vocabulary and rare words are also a problem, because if you don't have enough data to represent specific words, it's going to be really hard to predict them. And of course, we have a limited context and the bottleneck, which we'll talk in a minute. All right? Just to give you an idea, so neuro-machine translation went from a very incipient research activity to the leading standard method. So if you remember, the very first paper when we talk about this was 2014. The very first paper was published, and then 2016, Google switched from statistical machine translation to neuro-machine translation. And if you take that into account, this sentence right here is a little bit drastic, in my opinion, because it says statistical machine translation systems built by hundreds of engineers over many years outperformed by neuro-machine systems trained by a handful of engineers in a few months. It was not a handful of engineers. There's a lot of people working on this. It's definitely an understatement, but for sure it was less people than statistical machine translation. And if you might think, oh, yeah, like these people, how they didn't see that coming. This actually happened also before. That's not the first time, and this is happening right now again. So remember the rule-based systems? They suffered the same paradigm shift in which they thought those rules would account for every possible scenario, and then statistical machine translation came and said, ha, if you have enough data and if you have these features right here, you have this covered. And yeah, the rule-based systems, they pretty much died. Of course, there's still work being done with rule-based system there, but now they're more part of an ensemble of a complex system. They don't hold by themselves that well anymore. And how this is happening today, if you take a look by this large language models, it's pretty much happening the same thing, right? You don't see like vanilla sequence to sequence being used in this kind of architecture anymore. But you might think, okay, now that we have a context, we have encoder, decoder, I can calculate how faithful my decoder is, consider my context. You might think, is machine translation solved? Well, not exactly. So, and I wish I could reproduce all of this in 2019 and 20. I was still able to reproduce a bunch of them, so, but not anymore. So before, in the early stage from neuro-machine translation, If you're using Google, and this actually happened, if you say paper jam, it would be translated to Spanish as marmelada de papel, which it's pretty much you want to translate this here, and this is what you're getting from Spanish. And this actually happened. It was really fun to play with that in the beginning. Also, we would embed some biases and stereotypes in machine translation. We talk about this again later on. But depending, let's say in Malay, I don't talk Malay, but I want to believe that's the pronoun, how they use it. Depending on the profession or the noun that would use to categorize a specific pronoun, you would have that different. So, for example, if you say this word here is a nurse, and then here's a programmer, they would be translated differently. So if you have nurse, it would be translated to she, and if you have programmer, it would be translated to he. So that was a huge problem in the beginning, but again, this here, it doesn't happen that much anymore. The same thing for Finnish. If you have words such as nurse and cook, you would have the pronoun translated to she, and if you have doctor, fighter, king, leader, and all this kind of stuff, you would be he associated. What happened now, at least for most of the, let's say, the examples that we looked on, if you have something, if you have a translation that's grammatically gender specific, they would offer to you, say, hey, this language right here that you're trying to translate is gender specific, so you have these two options that they have coded there, and with reinforcement learning you can help the model get better and better. But then they leave this up to you to choose which kind of translation you want. Maybe also you saw that in a different form, in a way that you provide the sentence, the input sentence, and the output, it provides 2, 3, or even 4 translations. They say, hey, pick the one that's the best for you. And then you pick whatever that is, and this helps to improve the model. All right? This doesn't happen anymore. It happened until 2020 at most, in which, depending on the language that you're using, if you provide some gibberish, you would actually have some text that meant the thing. Why? Because in the beginning, those models, they use, for example, the Bible to be trained. So whatever you inputted there, they would provide whatever text with the highest probability they had. In this case, were texts from Bible and religious texts. This doesn't happen that often anymore, at least not for the examples that I play with. But in any case, so some issues still with the current scenario. We have out of vocabulary words, domain mismatch between train and test data, because while on the train you have everything aligned, when you get to test, it's not that trivial, because you can provide let's say, a word or a sentence that you're trying to translate, and you have no information about, I don't know, a specific word that you use. So you won't be able to produce a one-to-one translation in this direction. Maintaining context over longer text is simply complicated because of the bottleneck problem that we have here at the bottom. Low resource language pairs, they are still a problem simply because you don't have enough content to train these models. Sequence to sequence, and then later when we talk about attention, all these models, they require a lot of text. Simply, they have to optimize those weights a lot. So if you don't have enough examples, the random values that you initialize all this weight matrix, they won't produce a good output. Sentence meaning, it might be hard, and the pronoun resolutions as we just saw. So, as we saw, neuromachine translation research has pioneered many of the recent innovations in NLP deep learning. But again, this vanilla sequence to sequence, people don't use anymore. There are different alternatives and different architectures that are built on top of that, but one of them deserves special attention. This is why we'll talk about that. Attention networks. So what is attention networks? Again, we have our sequence-to-sequence model right here, and before we jump into attention closely, from attention, we're going to get to self-attention next 2 classes. don't get frightening, or like if you say, oh, here we use a self-attention, it's not that trivial. Like it's a bit different from normal attention and self-attention, but in order to grasp that on the Transformers lecture, we should take a look into this. But in any case, so we have our sequence to sequence architecture, and what we mean by the bottleneck, we already hinted that in a way that on the very last states that we have our encoder right here, we are hoping that this here will provide a faithful initial hidden state for all our decoder part in a way that this here will take account for whatever number of steps that we had before. And needless to say, this is a problem because this state right here, this last state in our encoder, it needs to capture all the information about the source sentence. And this here is a bottleneck simply because there is no guarantee that this mid state right here will contain everything that we need to represent our next sentence. So by using neural attention, we'll make it possible to integrate the actual alignment that we have not just by sentence and sentence, but at a token level. Before, we were aligning manually with statistical machine translation, words by words. Then we moved to a sequence to sequence in a way that I know that this sentence here relates with this other sentence, A and B, but now we can do this at a token level. So this technique, attention, is a natural encoder-decoder aligned. And on each step of the decoder, we're going to use a direct connection to the encoder to focus on a particular part of our source sequence in a way that every time I'm autoregressively predicting every word that I have, I'll have a sneak peek on my encoder and say, okay, from all these words that I have in my context, which makes more sense or which is more related with my decoder. And I'll do this for every step in my decoder with these direct connections, right? And how this looks like. So the idea is, we're gonna have our encoder as before, but when we start our decoder right here, we're going to use the hidden state from our decoder and our encoder, and we're going to produce what we call an attention score by doing the dot product between, in this case, since this is the first on the first state from our decoder, and we do this for all the steps in our encoder in a way that we'll produce these attention scores for every single step that we have in our encoder, in a hope that I will be able to associate this step for the next prediction with the one that makes most sense in my encoder part, all right? And the idea is after we do the dot product between the hidden states and our encoder and the first step in our decoder, we'll take the softmax to transform all this attention scores into an attention distribution. And by doing this, all this here, they have to sum up to 1. And I know that, and we know that the hidden state with respect to our encoder with the highest score will also be maximized in this softmax right here. So most likely, this very first word right here in this case will be related with the very first state in our decoder. And as, on this step, the decoder time step, we're most focusing on the encoder hidden state for I. In this case, is this prediction in our start step. And the idea is, as we move forward in our decoder for the new steps, we're going to have a different attention distribution in a way that for every new word that I have, and considering the hidden states, because this here will still carry around from the encoder to the decoder, we'll have this attention distribution change. So we use this attention distribution to take a weighted sum of the encoder hidden states, and then our attention output mostly contains information from the hidden states that receive the highest attention, in this case right here. So the idea is, after we look back at all the steps in our encoder, I'll use this attention distribution right here to help me do a better prediction for which word I'm going to predict next. So we concatenate whatever the attention output that we had in our encoder, considering this decoder right here, and then we do our prediction. For the next step, we do pretty much the same thing, but now we're not taking into account more the previous step, aside from the actual hidden state from our decoder, but we do the dot product again from the new decoder state with all the steps in our encoder, and our attention distribution will change simply because the word related in this second step right here most likely will not be the first one as we had in the previous example. The thing is, as we optimize this, and since we have the actual which word we should be predicting here at the training time, we're gonna be adjusting this weights that we are carrying around, all right? Also, sometimes we take the attention output from the previous step, so the previous step that we just calculated right here, and we use this together with the new hidden step to make our prediction. So depending on the architecture that you're using, you can either focus on all the encoder steps that you had before, or all the encoder steps accompanied by the previous output score that you had. And then we pretty much keep doing this until we reach the end of our sequence. And the same way as we had it before, at training time, we calculate the loss for every single prediction, but since we know exactly which word we should be having here, we just use the actual word when we're doing the training. And testing, of course, we don't have the target sentence. Okay? Different from the other architectures that we saw, we are not going to do any Jacobians or any partial derivatives right now. Some details to help you remember what are the steps that we are considering. We have the encoder hidden states from H0 to Hn. On time step T, we have our decoder hidden state, which is our S. And then to get the attention score for this specific decoder hidden states, we do the dot product from that timestamp, in this case T here, with all the steps that we had before in our encoder. After that, we take the softmax to get the attention distribution. So we take our E that we just calculated right here, which is the dot product between decoder and encoder. We put this in a softmax to get this attention distribution. And then we do a weighted sum between the encoder hidden states to get the attention output that hopefully will align our input and our output. In the end, we take that weighted sum that we calculated right here with the prediction that we have in our decoder state, and we use the output scores that we have with the decoder prediction, or in this case the decoder hidden state, to have our prediction, right? Some advantages, and I think, no, I put the disadvantages a bit after. So, attention significantly improves neural-machine performance simply because we allow our decoder to attain to specific parts from our source, from our encoder, and this is done kind of automatically. This solves kind of-ish the bottleneck problem. In practice, we have other bottlenecks. So, but let's believe that for now, the attention allows the decoder to look directly at the source, bypassing the last state that I had in my encoder. In practice, we'll see that it doesn't look that far away. It doesn't take into account the larger context that good as we wish for. Attention helps with the vanish gradient problem simply because now we have a shortcut to faraway states, so we are connecting every single step in our encoder with our decoder directly. Attention does provide some interpretability, but this here is both an advantage and a disadvantage. We'll talk later on. By looking at this output or this distribution scores that we have, you can say, okay, if whatever output that I have has the highest score on this part of my encoder, probably it's paying more attention to this part. And you can use this in test time to kind of justify why you have a certain, let's say, translation sequence. In practice, it's not that easy, and it doesn't mean that much as we would like to. Also, we already talked, we have an automatic direct alignment, so we don't have to take care anymore by, okay, this word has to relate from encoder and decoder directly. This is done automatically, simply because we know all the words from our input and our output sequence, all right? Yes. So attention is a great way to improve the sequence-to-sequence model for machine translation. And of course, you can use this in many different architectures, not just sequence-to-sequence and not just machine translation. We'll see that later on, we take this idea of taking a look from our output and our input, and instead of using these two sentences, we use the same sentence to see how the terms between that input sentence, they pay attention one to another. And this is pretty much self-attention, but we'll get there. Also, we sometimes say that the query attends to specific values, and this is the very incipient version when we talk about self-attention, that we will see that we have query, values, and keys. Think about this dynamic between your encoder and decoder, that you have some sort of a query, and that's your decoder, and you're looking back to retrieve specific values. And what are those values? The words that you have in your encoder. So this idea to use terms and weights, of course, as query, values, and later we'll introduce keys, it starts pretty much with this. So given, just to a more general definition of attention, given a set of vector values and a vector query, attention is a technique to compute a weighted sum of the values dependent on this query. So the weighted sum is a select summary of the information contained in the values, where the query determines which value to focus on. So every time I use my word in my decoder as a query, I can probe my encoder and see, okay, which word I have to pay attention and which value I want to retrieve. This is just the outline. We can actually go to more interesting stuff. This here is already repeated what we just said. It's just to help study on the summary. So the way we're calculating the similarity between the encoder and decoder, the way we present it with a dot product, is not the only way of doing this. People have tried to optimize and have a better representation for this dynamic. The way we just saw is the dot product, in which we multiply our decoder and encoder right here, as you can see the first one. There's also multiplicative attention, in a way that you also do the dot product between encoder and decoder, but you introduce a new weight matrix to that. Then there is another approach, I didn't put it here, in which they decompose this weight matrix and sub-matrix with a smaller dimensionality, in a hope to make this here more performatic, because not all the dimensions, they will matter, and this multiplicative attention. Then we have also additive attention, in which you multiply for specific weights your encoder and your decoder. You put that in a 10H, and then you multiply by another weight vector, arbitrarily initialized. Then there's other architectures, but this got more popular in self-attention, in a way that they discovered that there is no need, especially if you have larger sequence, that you have to pay attention or at least verify every single word in that context. So they come up with the concept of global attention, local attention, random attention, and so on. But we'll hopefully get there. But think as just improvements how to relate the encoder and the decoder that you have. All right? The initial idea, it remains the same. Then you might think, yes, we solved the problem between encoder and decoder, but attention technique also has its problems. First, it is really expensive to run that, because you have to make all the multiplications for every state in your decoder with all the states that you have in your encoder. This problem will get worse in self-attention. The attention mechanism, as we see right now, is sequential in nature, simply because at the decoder step, we have to calculate the attention scores for all the steps over and over again. The attention scores when we're multiplying the decoder and the encoder, especially if you're using additive and multiplicative interactions, they are sensitive to the length of input you have. So the larger it is, the harder it gets to control that, or the less meaningful it gets, at least for the weights capturing the sequence. Also, we'll see that although this attention mechanism allows us to attend to different parts in our inputs, in practice, we'll see that from the entire sequence, very specific parts are actually relevant for your prediction in the end, which they'll have a really high score there. Needless to say, and we talked about this already, we do require a lot of training data for this technique/architecture. Also, and we talk about this on advantages, although usually you see attention scores being used as a proxy to understand where your model is paying attention, in practice is not that meaningful. It's debatable. Yes, you have a distribution of high scores for whatever parts that you have in your sentence, but what actually that means is debatable in a sense that, is it really showing to me that this relationship between two words are simply represented because I have a higher score between those two parts? Think as, and I'm really going far on this comparison, how many of you already were looking to word clouds? Everyone loves to do word clouds. What do they mean? Yeah, you have a blob of words. Some words are bigger, smaller, but yeah, it looks nice in a website. But if you want to make your point, like, yeah, it doesn't mean much. What usually it's going to happen is you see papers with fancy heat maps to show how the attention is changing over the layers. Yes, it gives you a good hint to, okay, if the model, the sequence are not pay attention to specific sequences, maybe that's not that relevant. Yes, but don't base your entire discussion simply because you have a fancy heat map to illustrate these attention scores. Okay? And before we move forward, if you remember the beginning of the class, we talk about how machine translation is problematic, not because it's hard to capture all the semantic difference between input and output or source and target sequences, but also about the evaluation. And this is valid for pretty much any task that involves generation of text. They are based on very specific metrics. Everyone knows that they suck, but they still use them. There are better metrics nowadays that they try to grasp, okay, how faithful one translation is or how it conveys a specific meaning. But in practice, if you have those systems and you don't validate with people, it can have the highest score you can think of it. If it's not a good translation, people will not use it, and it's not reliable. As simple as this. So for those thinking about working with machine translation, or any text generation task for that matter, make sure to always have a qualitative analysis in whatever experiment that you have to at least validate if it's indeed working for humans. So that being said, this huge caveat, we have to take a look on those automatic metrics simply because people still compare with them. But keep in mind that's not the best proxy. So we have blue right here, which is pretty much, we're going to take a look on the translation that we have with some references. And this translation is usually done by human, which is also debatable if human is actually the best gold standard. Spoiler alert, not always. There's papers on this, and I should include this. I'll make a reminder for me. And then, okay, but how we calculate that? Let's take a look. So pretty much, we calculate the precision between M and WT right here, where M is the number of words for our candidate, and this here is our sequence that we are providing, that we're machine translating, with some reference that we have right here. So we divide the number of words that from our candidate appear in our reference, divided by the total number of words that we have in our candidate. And this is a really good example how a metric can mislead you. In this case right here, we have a candidate, and then by taking into account our reference and how many words from our candidate appeared in our reference, we get a score of 100% on this translation. Awesome, right? Not really. There is modifications on the blue score in which you can have bigrams, trigrams, fourgrams, and so on and so forth, but they all suffer from kind of the same problem. In a way that, in this case right here, we are considering all the bigrams that we have in our candidate with respect to our reference. So in this case, we have the and the, and of course this never appeared in our reference, and the cut appeared in this here. We're using the first reference as a reference. And then we see here that the score is still 50%, which is pretty high, if you ask me. Needless to say, this here can generate some problems, especially when you're using a system that's not that easy for you to track those errors, and you're relying on this automatic measure to take a look on how good your translation is. As we saw, blue has some problems. Aside from the metric not being a faithful proxy, in this case specifically, translation is not that simple. How many times you had to translate something from German to English, you simply say, nah, there's not a direct translation to this. So imagine for you to code that into an automatic metric. Yes, so you'll see this virtually in every single paper using this kind of metric, and you might think, well, okay, it's not a big deal, it's just a score for a sentence. The thing is, the moment that you have those automatic translations doing by the systems, you have to score what is the most probable sequence. And stuff like this happened. So this was in 2017 that Facebook translates good morning into attack them, leading to an actual arrest. And needless to say, this is quite problematic. So just an excerpt from this news. So police officers arrested the man later that day, according to Israeli newspaper, after they were notified of the post. At no point before his arrest did any Arabic-speaking officer read the actual post. This is, by the way, is automation bias, in a way that you simply agree whatever automatic score output you have, because you say, well, that is generated, it must be true, right? It's on the internet, it must be true. So it's pretty much the same idea. And of course, they took care of the matter, but you can see how this can be a problem. All right? And then you might think, okay, the metric is pretty much terrible, what we do? There are other alternatives. So usually when you're working with either machine translation or again, text generation, you have a bunch of metrics being used. Blue, NIST, Rouge, Meteor, F1. Now you have kind of a BERT score and BART score, which it's kind of a way to introduce cosine similarity to those measures. They do work to some extension, but still they're far from perfect. We have NIST, it's National Institute for Statistic Technology, it's the same name as the institute in the US. We have Rouge, which is a modification of blue. Instead of taking care, instead of looking to the anagrams in the reference translation, in the reference translation instead of the other way around as we did for blue. By the way, we will revisit those metrics when we talk on text generation in the lecture with Frederick. There, he uses more, it's called Rouge 1, 2, 3, L for the longest sequence, BART score, BERT score. We'll take a look on this later. We also have word error rate, which accounts for substitutions. We also have the Meteor score, and so on. There is this actually really nice post about Rachel Tatman, in which she goes and gives examples why you should not trust only on blue and whatever task you are accounting for. But you can take a look into this, okay? That being said, we can close this lecture.